Maybe you are asking yourself what this means, function modeling 6150, because when you have been working with 6150 up to now, you have seen logical nodes, logical devices, IEDs, but not too much talk about functions. Naturally, if you read the standard, you find very often the notion of function, different part of the standard. This function modeling is very much related to engineering, also entering a new area. So what I'm talking about today is not how to do 6150 engineering, because we have thousands of systems worldwide in 6150. I want to talk about more efficiency in it, because it's obvious if you talk to people which are doing projects, so there is very different feedback. Project engineers which are making big projects, they are very often happy with the performance of GUS, with the possibilities GUS gives them. They are not so happy with interoperability always, and they are not so happy with the workload of designing and getting these 6150 systems up and running. So we come to the point of engineering efficiency. To gain this efficiency, exactly we have to do things differently from before, and 6150, the standard itself, is providing the means to it. We just have to take this into the hands and do it. Independently, if you are talking about the new challenges in the distributed areas, or as we have seen in the substation-to-substation communication or wide area networks, where the systems become much bigger with much more IEDs, utilities have always a quite similar basic process. So they have one activity where they deal with their concepts and the definition of their standards. So utilities have departments where they work on just documentation standards, on design standards for the system, on communication design standards. All this work has two purposes. One purpose is that when it comes to projects, they want to be more efficient, they want to have standardized solutions. But also when it comes to negotiate with the suppliers, the manufacturers of the relays, the system integrators, then they want to be able to have more control over deliveries by making frame agreements, having predefined IEDs delivered, and these things. So this is a standardization and engineering phase which is independent of any project. Once this work is done, then the utilities, if they do the project themselves, or the system integrators, they take over for a particular project, and someone creates a specification, someone designs the system, and it's commissioned and tested, and it goes into maintenance. So the standards are applied to each automation project. And when I want to talk about functional modeling in 6150, I'm talking about both processes, not only the project engineering process, but also the standard design utility. So when we want to improve this process, independently if we just make a substation or an area solution, then we have some key factors which will allow us to do this improvement. And for utilities which made the experience that, let's say, they have bought in the last 10 years turnkey 6150 systems, and now they see that they got deliveries from different system integrators or even from the same system integrator, where the solution are very different, which is very hard to maintain. One key is that the system integrators are delivering similar designs for similar substation automation systems. This sounds a little bit hard to do, because if in similar substation automation systems different IEDs from different vendors are used, we have interoperability, we have 6150 communication which works, but the detailed design of the signals, also sometimes of the schemes, depends still very much on the relay of the particular suppliers. So this is a challenge to get similar design for similar SA systems. When we want to standardize, then we need to be able to efficiently specify, design and document these uniform systems. Once the system is specified, we would like to have this specification more or less independent of the different vendors. So in a frame agreement, maybe a utility is focusing on certain vendors and certain relays, which last then for 5 or 10 years. But generally there are different vendors, and the relays change with the time, but the primary equipment and the algorithms and design solutions of the utility, they they remain stable, independent of the IED. If you think about distributed systems or monolithic system, also there we have system design, we have algorithms, we have signal lists, but we do not have specific relays anymore. So it's important that our solution is vendor agnostic or even independent of the hardware of the relays. So we should focus on the protection and control domain. With this, we come to the next point of efficiency, that we need to formalize the specification and the design. Formalizing allows us to automate the configuration. So if everything is formalized, we can do automatic processing. We can have very rich implementation details. So up to now, when the utilities are writing specifications in Word, the worst case is deliver a 6150 system. But also if there are detailed descriptions of the functions, then a lot of design decisions remain with the system integrator. If the utilities are able to make a much more formalized specification, then a lot of the design decisions can be already given by the utility and reduce the freedom of the system integrator. And finally, we have similar solutions for similar substations. But once we have this formalized specification of the system or even formalized design of the system, then when the system integrator delivers the system for the SAT and FAT, then SAT and FAT validation tasks can be done by using tools. So before making all the point-to-point tests, formal validation can save a lot of work in this area. So to summarize, the key factors to improve the engineering process of the systems is that we have standardization, that we have this standardization in a device-independent way, and that the standardization is not written text, but it is in a formalized language, like for instance done in SCL. We have seen the key success factors. What has this to do with 61850? Or how can we implement this functional modeling in 61850? Before we answer this question, let us have a look at the content of all the SCL files which are defined by the standard. All SCL files independently, if we talk about ICD, CID, SSD and so on, they have all a similar structure. They have a substation section, they have an IED section, they have data types, and they have information about the network. The difference between these files is not so much the specific content, it is more which content is used in which phase of the engineering. Not very often used, not yet, is the substation section. And I have already indicated just an example of a hierarchy in the substation section where we end up with a circuit breaker in the bay of a substation, and the circuit breaker has a certain function which is related to some logical nodes here. We have other sections where the IEDs are described, so that is something where we are familiar with. IEDs have logical devices, and the logical devices have logical nodes, and we have also the communication configuration in this. We have data types. The data types, they give us detailed information about the data which is related to the logical nodes. In this case, I've indicated that the type definition is related with the logical nodes on the substation part. So here we are independent of the relays, of the IEDs. And we have a network section where all the IEDs are connected. And also here, with the new edition of the standard, we have to think about linking subnets and the Airbus, which is spanning different networks. So this is basically the content that we have in the SCL files. How can we use this to improve the efficiency of the engineering? If we are using the SCL language, what can we reach with this? So I've shown here the first part of the representation before. And if we want to formalize the specification and the design, then we can use this part of SCL. And this works naturally inside the substation. It is shown here, but we look at edition 2 of the standard and 2.1, which is upcoming. Then we also have a generic process element, which allows us to describe windcraft and DAR systems. process element which allows us to allocate several substations in one process, which allows us to describe power lines between the substations. So we can today model in a device-independent way our power system completely in 6150. It is very close to SIM. The difference is here we are really focusing on the logical nodes at the end. So this can be used to formalize the specification and the design, something which is not really very often used in projects today. And as you can see, we are independent of the IEDs. And in this way of thinking, it is not so much the logical nodes which are at the center, because you can imagine in a high voltage feeder, you have easily 100, 150 logical nodes, and the granularity of the logical node is not really good for this modeling. That is why we have functions as an important element in the substation section. In the IEDs, we do not have functions. In the IEDs, we have logical devices which are grouping the logical nodes. In the substation-based modeling, we have the functions which are grouping the logical nodes. So these functions in SCL, they are the container for logical nodes. They are the device-independent containers. These functions, they can be allocated on each level of the primary process. We can allocate a function as shown in the example before with the circuit breaker, for instance. We can allocate it on bay level, we can allocate it on station level, we can allocate it on a process level if we want to describe a wind turbine, for instance. These functions themselves, they can be hierarchically structured. So we can have functions and sub-functions. This hierarchical structuring can be used for different purposes. So sometimes the people are coming and say, I have as a base protection functions for the substation. Then I have distance protection, overcurrent protection, differential protection. So there's a classification scheme for my functions. This classification scheme may make sense when I build function libraries. So there I can use a hierarchy. I can have a hierarchy in the measurements, current measurements, voltage measurements, for instance. Then these functions can be used as building blocks for higher level structures. So when I want to build a bay type, so a typical feeder, high voltage feeder, incoming feeder, outgoing feeder, then I can compose this feeder with the single line and allocate to the single line the set of functions related to this feeder. And finally, then this set of functions contains the logical nodes on specification level. All this is done without thinking even about physical relays. Where do the functions help us? Substation sections that I have presented, this is present in 6150 since edition 1. But basically no one has really used it. There were several reasons for this. One reason is naturally the people were focused on the IEDs and getting the solutions done with the IEDs. The other reason is that this SSD, system specification description, that can be created out of SCL does not up to now contain really enough information to describe a complete specification. People wanted to apply this in reality, then there was a lot of work related in doing the model, but not all the information could be really covered, which was needed in real engineering. Now we are starting to overcome this, and what I want to show here is a very important principle. So we have such a system specification description file which uses SCL to define the primary process. At a certain point we have the function which itself then contains a couple of logical nodes. These logical nodes, they are related somewhere with the relay in the implementation, but on the specification level, this function can be used as an important link to a lot of other things. In the workshop tomorrow, you will see how we combine the functional approach here with the engineering of the HMI, for instance. So function can be related to information about data points and data flow, and based on this, HMI and gateway can be configured so we have data related to the engineering, which is not represented in 6150, but which is allocated to 6150 by the means of these functions. We can go a step further. We can have somewhere just plain documentation of the functions, and in a formal way link textual parts with the formal defined functions in SCL. And if we apply such the principle, then our 6150 SSD or 6150 primary structure is like a Christmas tree, which gives us the structure for all our specification work, and we just put in, like the Christmas bullets on the tree, we put in the different information from very different areas. Once we have implemented such a way of thinking and working with the information, then we can use this to be much more efficient in the engineering process. That is the next part I want to talk about. How is this applied to the engineering process? So this is the way how today the utilities are doing their standardization. So on one side they have tools like Excel, Visio, AutoCAD, MS Word. There are surely also a lot of other tools, and people are using these tools to create their standards. They make specification, design standards, function descriptions, I/O lists, and a lot of other stuff related to communication. It's obvious this is not standardized, it is not formalized, and everyone does it in its own way. And to come from such textual descriptions to engineering files is quite a long way, and what has to be done in between. If you are using the principle that I've shown at the beginning to do the same work, then we have a kind of 6150 specification tool which is aware of the formal representation in SCL, and then we can use this formalized language to define our function types, which contain the logical nodes, which are grouping the logical nodes. These function types, they have, via the logical nodes, references, detailed references to all the data. So we have all the 6150 naming, the object names, also information like the functional constraints and what can be sent in communication and what not. We can have a combination of all these function types on up to higher level bay types, which will allow, if this is put into the library later, to specify a system just by picking up complete types, and with these types all this underlying information comes. And something which is also based on a kick and push that Alex brought into the standardization, we can use this representation to specify relays, to specify IEDs. So utilities make formal IED specifications, so-called ISD files, IED specification descriptions, when they negotiate the frame agreements with the suppliers. So these are examples. There can be a little bit more behind this SL representation. And once this work is done by utility, then they have a formalized representation of their specification, and they put this into specification and design libraries. I say here specification and design libraries because you can imagine to have complete relay independent specification using this part here, or you include already relay details because you have a certain set of relays you're going to use, and then as a utility you have such a library or as a result of your standardization work. And naturally these formal representations will drive the negotiations with the suppliers when it comes to the frame agreement. So now we are away from fuzzy Word Excel based specification and documents, and we arrived at some formal representation here. So this was the part of the standardization work. Now what is the impact on the projects? And the impact on the projects, once this is done, is huge. You remember the sentence that Alex had on his slides about the Russian system, where there was told that the opportunity is there with SCL to automatically create a system. If you have such libraries, then you can do this. But first, let us look on the classical process. This picture shows how I think probably 90% or 95% of the 6150 systems today have been engineered or are still engineered. So what you have is the three phases. We have informal specification phase, which is done by the utility. We have a more or less informal design phase, where the system integrator builds the system, defines about the functions, defines the signal lists, combines everything into the relays. And then we have a bottom-up engineering phase, where this is built, where the relays are configured, where this is implemented in the relays. Now, This informal specification is again done with the well-known tools here. It's based on the design standards that have been also made with these tools, and somehow the system specification is done. Some utility have already a very sophisticated system based on this. They have really put in a lot of investments to make such a system working. Then the documents are handed over to the system integrator. And the system integrator is very often doing also this the design in Excel, but because he has to deal with thousands of signals, very often you find that the system integrator side Visual Basic applications for Excel, or also some specific tools, let's say to extract signal lists for the gateway configuration, to extract signal lists for the HMI configuration. But more or less, this is also an informal design where the standard is really excellent work. And then the system engineer knows what he has to do. Then he goes to the shelf, takes the IDs from the shelf, and with the ID tools of the different vendors, he is just configuring the IDs. So he looks, what signals do I have for this feeder, what GUIs do I need to implement, and then he does this on the ID level. If he is a little bit progressive, then he has read the standard, then he says, oh good, I take the system tool, and I take the ID tools, and then I do this with the system tool. But when he tries to do this, and he has a system with about 100 IDs, and the first time he has made with the system tool an SCD file with 100 IDs, and tries to load this into a relay tool, then you will see that it is really too much work to do this. But basically the people fall back to a purely CID-driven engineering. It's obvious that if I have hundreds of IEDs, if I combine several substations, it is a very lengthy and error-prone work to make publishing and subscribing for each IED. In a lab environment, this works very well. I can make interoperability between 4 or 5 devices using the relay tools, and after a couple of hours or days it works. In a big system, it's really very, very hard to maintain and do this. So that is the reality today. And even with this, people are happy very often with 61 and 50, just complaining that it is too complicated here. What can we do now based on the functional modeling that I've presented? We can aim for such a process, even if there are some things to consider what the granularity and details means. So this is the ideal world. Somewhere we have a specification library which is completely independent of the relays. It just has logical nodes, also signals, functional decomposition of our system according to our understanding. With the system specification tool, we can pick up our default solutions from this library and create a system specification description for the engineering. If we have pushed a little bit further our standardization, and if we have added some real IEDs and the mapping of the real IEDs to our specification world, we can pick up the engineering solutions with the system configuration tool. And because in these libraries we have also specified all the communication needs, we have the information in this library that a position needs to be transmitted to the network control center and the position needs to be transmitted to the HMI. We have in these libraries also the information for a certain protection scheme. The protection start element has to be sent to another function. So based on this communication specification, the system configuration tool can automatically just create the complete communication configuration, so that all the work that we have done here manually, which takes a lot of time, is more or less automatically done out of these libraries and then transmitted to the IED configuration tool where the CIDs are created. This is the ideal process. We can do it for smaller applications today without a big problem with all the different vendors. So edition 2 supports this really now. If we have very big systems with more than 100 IEDs, this still is a little bit clumsy, so there we need maybe some additional ideas. But based on such a work, we will have much, much more efficiency. And the key of this efficiency is to have all the engineering knowledge in these libraries. So it has been done once, it can be reused, it is formalized. and similar substations really result in similar solutions, which is very good for the maintenance. So to summarize this, the 1650 function modeling with the use of proper specification tools will increase the engineering efficiency, and the key success factors for this is formalization, standardization, and the solution libraries. Without the solution libraries, we have to repeat this work every time, which doesn't make sense. Thank you. So we have left